Today we'll finish tunnels and other things and a bit of distance vector, and we'll meet again tomorrow for the very last test of 2018, and we'll meet again next year on a Saturday morning for the final exam. The next topic is tunnels. Tunnels is something that has been existing for a long time and is completely orthogonal, foreign to the architecture, but it's so easy to do that people did it. A tunnel is when you start carrying packets inside packets, for example, an IP packet inside an IP packet, or even an Ethernet packet inside a TCP segment, or whatever. Let's see a justification and how this arises. Assume here we have you, perhaps, you want to build a private network, but your devices are in two sites, and you have private IP addresses, for example, 10.something addresses. You want to interconnect them. How can you interconnect them? Well, if you don't care about security, we'll talk about that in a second, you can rent a leased line from an operator or pull cable, but that will be, in most cases, extremely expensive. So what you can do is have a modem connect to Swisscom or Simscom, and then use that here. But of course, you cannot simply use your private IP addresses. You could simply use a public IP service, but the problem is your addressing scheme here. How can we do that? Well, we can use what is called an IP over IP tunnel. So you buy special software in your routers, A and B, called tunnel software, that has the effect of opening a virtual interface. So here you have a physical interface, which is your Ethernet or ADSL connection to your provider. And you build a second logical interface here that connects via the provider to B here. So in order to configure this interface, you need to know what is the IP address of the other end of what is called the tunnel. And then the IP packets from X to, or from this side from X to S, for example, will be carried inside IP packets in this link here. So what we have done is, in fact, we have created a logical link. It is as if we would be pulling a cable from A to B, but we don't really need a cable. And after all, that's the goal of the network layer, to give the possibilities for any two systems to be able to communicate. Right. If we do this, S sends a packet using these mechanisms to some systems here. We observe at point O the packet. We do a Wireshark at this point here. What will we see? And the majority says A, large minority says B, but both are wrong. What will we see in reality? We will not see UDP as protocol type. We will see an IP packet that contains an IP packet. So we will see two IP packets, one in the other. We will see an outer IP packet that has the job of transporting another IP packet to the destination 111. So the destination address is the router A. But of course, inside this IP packet, you have another IP packet, which will have destination address, for example, 10.11.1 here. So it will not be visible unless you go to the second IP header. And the side effect of that is you have to signal to the outer IP packet that what it contains is an IP packet. So the protocol type will be the protocol type for IP itself, which is 04. So it will not be UDP. Of course, inside the second IP packet, you will see protocol type UDP, for example, here. This is what can be done in simple cases. Very often things are a bit more complicated for two reasons. One is a bad reason because of the middle boxes that typically kill everything that is not UDP or TCP. So they kill very often IP and IP packets. which is stupid because the fix is very simple. You simply put UDP, and inside UDP you put the IP packet, which you can do very easily. Remember, there are still systems that are not IP. They tend to disappear, but they still exist. So you can use tunnels to carry Ethernet packets, in fact, or packets of any type. So there is another layer here, another header, which is called the L2TP or the PPP header, that is essentially indicating what kind of protocol is carried, very much as if it would be within an Ethernet packet. So typically, when you use this form of encapsulation, this is called encapsulation, you carry this additional information. So you have an outer packet and an inner packet here. In reality, if you interconnect your two sites via the public internet, you probably want to add some form of security in the form of encryption and authentication. So if you use this, you typically add another layer, which is, for example, there are multiple possibilities. One of them is IPSEC. IPSEC stands for Security of the IP Layer. It is a set of mechanisms and headers that explain to you how you can, which authentication and encryption mechanisms you can use and how to encode which one you're using. So if you do this, then you will have an IP packet which is now completely encrypted. What is not encrypted and will be visible to the outside world is the fact that you are carrying an IP packet and how many packets you carry, but the content will be completely encrypted. So this is one of the two forms of VPNs, virtual private networks, which uses this mechanism. There are other mechanisms that can be used. Instead of doing this clumsy layering of UDP, L2TP, and IPSEC, or IPSEC is not clumsy, but this one is clumsy, you can do a more radical thing by opening a TCP connection between A and B, adding security on top of it, which gives you TLS. And on this TCP connection here, you put all your traffic. This is very often done. This is systems like OpenVPN that do it. Right? What is the difference if you use this or that, apart from the protocols? We did a module on congestion control. Right? If we use this system, we use UDP traffic. The tunnel is not at all is not congestion controlled, right? So if you do this, you typically want to add a mechanism for rate controlling the tunnel, saying at which rate, which amount of traffic you want to send. We've seen that in Mininet. We have seen mechanisms to artificially reduce the rate at which some traffic is sent for somewhere, for example. So that will be something that is needed here. It's not often not done, but if you don't do it, you're just sending UDP traffic without control, and we know that can cause problems if there's a lot of it in the internet. If you use this solution here with TCP, the traffic will be congestion controlled, but you will be one connection. Right? So if you compete with a bottleneck here in this network, you're treated as one connection. So if you have other people somewhere that are using a lot of traffic here to go to YouTube or somewhere on the web, you will be competing with them, so you might not get a lot of traffic here. So there are traffic problems, congestion problems that are related to that. It is typically either done by small volumes of traffic. That's what you will do if you go home and activate a VPN, an EPFL VPN system. You will use probably this one. Not congestion control, but nobody cares. If you are truly interconnecting big sites of the Nestle company, for example, through public operators, you need to care about congestion control. And this is typically done by having other mechanisms that we don't see in this course, that we will see in other courses that have to do with class-based queuing, like we've discussed at the end of congestion control. The operator in such a case will guarantee to you some quality of service, some minimum rate between A and B, by using mechanisms of explicit rate control, which are simpler than what TCP does. Here is an example when you go home and connect to the EPFL VPN. I'm doing here an interface, I'm showing the interface configuration at A, which is a computer connecting to the VPN of EPFL. We see that it has an IP address. It participates into my local area network, so it has this address and mask. Then we open here through VPN mechanisms a tunnel that ends here, so the two ends of the tunnel are my PC and a VPN router, that's the name we give to such things, that is offered by EPFL. And for the operating system, it has the effect of showing a second interface, which is now a virtual interface. There's no physical mechanism. It is the same interface as I'm using here, Wi-Fi or Ethernet. But this second interface has now an EPFL address here, right? Here a subnet mask of 32 bits, which means it is a point-to-point connection between me and the server here. Assume I'm doing this, and B sends a packet back to A. Now, because it sends a packet back to A, B is sending at EPFL, it sends to this destination address. Now, if you do this, it is to be able to participate with EPFL systems as if you would be inside EPFL. So for B, your destination address is this one, is an EPFL address. So B will send it towards this. Now the subnet 83 is the subnet here on which the VPN router is working. So it will go towards the VPN router here. Do we need to do something else? I'm proposing possible options. What do you think? And the correct answer is, well, let's see. Does B need a host route to A? No, because A appears to be in this subnet here. So if R is leading to this subnet, for the rest of EPFL, packets to this destination inside EPFL will end up on this subnet here, right? However, there might be an issue due to the MAC address. When R sends the packet towards this destination here, in fact, it should send it to the VPN router, but it's not the EPFL, it's not the IP address of the VPN router. It is another IP address here. But we have seen a solution for that, it's proxy ARP. So here what we do, in fact, we are creating a virtual link on the VPN router that goes to A with this EPFL address. So we see that the subnet 83 is on both sides of the VPN router. And we know that in such a situation, problems can be solved by host routes in the VPN router, which certainly the VPN router must know that A is on this specific interface here, on this tunnel interface here. So yes, it must have this information, but that's part of the VPN router, of the VPN server function. And then the other part is the ARP problem, which is solved by proxy ARP. So that is tunnels, and the main use today is VPNs, but also, as we will see, can be used in the interworking between IPv6 and IPv4. We know that IPv6 and IPv4 cannot communicate. We have seen already some mechanisms for helping their communication, which is application layer gateway, but that's a heavyweight mechanism. We will see now better mechanisms by studying a number of problems that exist, essentially 3. The first problem is what I call 6-to-6/4. That's the problem we have when we do the labs in the Internet Engineering Workshop, and EPFL, surprisingly, does not provide to us an IPv6 service to allow to connect this room to the IPv6 Internet, and gives to us only an IPv4 service. What can we do so the problem is I have a local area network that runs IPv6 and would like to talk to other systems that also speak IPv6. So the problem is really the provider access is only IPv4. That's your problem at home if you want to do some exercises with IPv6 and you have only IPv4 from your provider as well. There is one easy solution, widespread solution, which is called tunnel broker. A tunnel broker is a company, an internet service provider, we use, for example, Hurricane Electric in the Internet Engineering Workshop. You can try it. You can do it from home, and then you will have IPv6 from home. What it does is this provider has an IPv6 internet, and in fact companies like Hurricane Electric are very aggressive and try to show to the rest of the world that they are leaders in IPv6 connectivity and IPv6 service by counting the number of customers they have, and the way they have many customers is to provide tunnels. So they provide a router, it's a bit like Homer's router a few minutes ago, that is connected to their IPv6 internet and is also connected to their IPv4 internet with a well-known address, for example, 1234. Then if you want to interconnect your PC or even your entire local area network, you ask them to get a tunnel. What will they do? Well, they will give to you an IPv6 prefix, for example, this one here, 2001.123/64. So this company gives you a prefix as if you would be directly connected to them. In addition, they also give to you an IPv6 address for the two ends of the tunnel, one which is on their side, one which is on our side here. And then, from then on, they accept, and you have to configure your router here, or your computer, if you do it natively, with a virtual interface. And it's the same as what we did before, except now the outer packets will be IPv4 packets that will carry IPv6 packets. So it's exactly like before when we had Homer's network with two private set of IP addresses. Here they're not private, they're IPv6, and they are carried over a tunnel, which is the IPv4 packets carrying IPv6 packets. So this is, I would say, the most standard solution that is used. It's very simple, but let's try to see if it is so simple by answering a few questions. Lisa is here on the right, sends a packet, so from right to left here, we go this way, and we observe the packet at number 1. What will we see? So let's see all those possible answers. For the rest of the world, if this mechanism works, when we are in the Internet Engineering Workshop, when we do a ping or trace route to an IPv6 site, for the rest of the world, they don't see a difference. They don't know that we are behind a tunnel or whatever. Right? So what we should see here is a regular IPv6 packet, because we are in the IPv6 Internet, and the destination address in an IP packet is the final destination. So it should be this one. So the IPv6 destination address is this one, at point 1 here, certainly. Not this one. If it would be this one, it would mean we're going here, but then how do we go from here to there, right? Also, we don't have an IPv4 packet here at this point. If we look at number 2, we will see an IPv4 packet, but at point number 1, we will not. Remember, a tunnel is like a logical link that replaces a physical link. So here what we've done is simply we've pulled a long cable between A and B, except that it's not really a cable, it is just mechanisms through the IPv4 internet. But for IPv6, this is just one hop. One very long hop, possibly. If Hurricane Electric is in North America, that may be very long. But it is one hop from the IPv6 viewpoint. So the correct answer is D here. Only D is the correct answer. Now assume we want to do path MTU, which we do path MTU discovery, which we do, for example, because we don't want to take the default MTU value for IPv6. We want to make it a bit larger. So if we want to discover what's the path MTU between Lisa and Homer, what will we see? Assuming all the links have standard MTU of 1500 bytes. The correct answer is B. So path MTU is the size of the IP packet, including the IP header. Right. That's the definition of the MTU. Now, the MTU here is 1500 everywhere, except now this packet will be for this link. This link here, which is now a virtual link, is carrying IPv6 packets inside IPv4 packets. So the path MTU is from the IPv6 viewpoint, what is the maximum size of an IPv6 packet that I can carry in an IPv4 packet. The IPv4 packet itself can be 1500. There's 20 bytes of header for IPv4, so it's 1480. So the correct answer is this one, if there is a native encapsulation as we have seen. If we do VPNs like we did a few minutes ago with encryption and a number of things, then the path MTU will reduce considerably more. So you can lose typically 100 bytes in VPNs compared to what you have in regular networks here. That shows one of the reasons for having this MTU problem is tunnels and encapsulations. Well, that was the easy part of how to use tunnels to solve some of the problems of IPv4 and IPv6. So I recap, the things we have seen today so far is how we can access the IPv6 internet with an IPv6 machine or an IPv6 local area network when our provider gives us only IPv4. And the solution is find some nice provider who is nicer than our provider, because our provider gives us only IPv4, who accepts also to give us a tunnel, to dedicate to us some of their resources on their tunnel broker, on their tunnel server machines, and then we will have this access via them to the internet. Now let's look at another type of problems that does not use tunnels, but translation. XLAT stands for translation. That's the American acronym for translation. So what is the problem? The problem is the converse is 424/6. So assume you are sitting at home over IPv4 because you're old and conservative, and you want to access some IPv4 hosts. Right? But your provider gives you only IPv6. Bad luck. This is what happens, for example, or will happen, starts to happen in some regions of the world where some providers for some services, typical cellular telephony, will give you only IPv6 access because they don't have enough IPv4 addresses to give to everyone. And now, assume you still have some IPv4 stuff that you want to run and you want to access some IPv4 services. Another example could be that perhaps you have IPv4 and IPv6, but you want to connect to some applications that run IPv4 only, like Google Scholar, for example. In that case, you can simply run your IPv4 software because your host and probably your local area network at home does both IPv4 and IPv6, so you're back to the same problem here. So how can we do that here? One solution could be to do tunnels, and some solutions have been provided, but as we'll see, there is a smarter one which uses translation. So there are multiple solutions, but this is, as far as I know, the most widespread one today. So this solution is called 464 translation, 464 XLAT. 464 explains exactly the configuration. We have an IPv4 machine that wants to talk to an IPv4 machine, but in the middle there is only IPv6 connectivity. So for that to happen, you need to have a provider that helps you with this. So your provider has the problem. It's your provider that does not have IPv4 addresses. So they still want to help you and solve your problem of IPv4 connectivity. So your provider will do the following thing. It will do three things. First, your provider will reserve a block of addresses, this one here, which is typically a /96, which is a block of IPv6 addresses that represent the IPv4 internet in this provider domain here. So I put it here, which is show a place where this provider has a router that interfaces both IPv4 and IPv6. And for the inside world of this provider, the IPv4 internet is mapped to this space here. /96 because, why /96? Well, because IPv4 addresses are 32 bits. So if you have a prefix of 96 plus 32, that gives 128, which is an IPv6 address. So that's the first thing that the provider needs to do. The second thing that this provider will do is for every customer, like Homer here, he will allocate a block of IPv6 addresses for this customer. For example, this block here. We could allocate a /96 if we wanted this provider to, this local area network to use only IPv4, but typically you have IPv4 and IPv6. So we give you a block that's a bit larger, and inside this block you will put all your IPv4 addresses, plus also your native IPv6 address. So that is business as usual. If you're an IPv6 provider, you allocate to a customer a prefix that allows this customer to make its own networks. That's the difference between expectation with respect to IPv6 and IPv4. With IPv4, we get from a provider one address. With IPv6, we get a prefix, which is much better. We can build our own network, and we don't need NATs in principle. That's the second thing. Then the third thing is this provider, and that's the ugly part of it, needs hopefully to still have, it doesn't have enough IPv4 addresses to give to anyone, to everyone, but it still has a block of IPv4 addresses. Here, for example, I'm assuming it is a block, a /24. So a block of 255 addresses. This provider has perhaps 1 million customers, so this block is much smaller. If this block would be large enough, the problem would not exist. But if this block is typically much smaller. And this block is used to represent all customers like this one in the IPv4 internet. So we need those two blocks here, the blue block and the red block here to represent the remote IPv4 and the true IPv4, and here to represent the IPv4 in the IPv6 world. Right. Then some of the things are easy. For example, if Homer is using an address like 10.1.2.3, then the packets that go toward this direction will be translated by this box, which is the customer address translation called CLAT. It will translate the IP header. So here it receives on one side an IPv4 packet. On the other side, it will issue an IPv6 packet. It's a bit like a NAT. A NAT has on one side an IPv4 packet. It manipulates the IP addresses on the other side. But here the manipulation involves changing the type of address and the type of the packet. Therefore, it was an IPv4 packet. It becomes an IPv6 packet. So after all, it is doing the original thing we would have hoped. We would have hoped that IPv6 is just the same as IPv4 with different addresses. So here, this is what this CLAT is trying to do. So when a packet comes from this, 10.1.2.3, it will be transformed into an IPv6 packet here with a destination address, with a source address that will be this prefix here, the red prefix allocated to Homer's network, with some mechanism to map the green addresses into the IPv6 addresses. For example, we can map them one-to-one by writing, so A is 10, 1, 2, 3. So this is 10, 1, 2, 3 that is written in the last bit of the IPv6 prefix here. So this is what will be for the source this address if Homer is sending a packet to Lisa here. Now the destination address, so the packet that Homer is sending a packet to 9.8.7.6. Then, remember, we have this block that represents the IPv4 internet. So this CLAT knows the block. So the block is allocated by this local provider. So it knows this block. So whenever it receives an IPv4 packet from the local network that has destination, this blue address, it will map it using the block that's reserved for mapping the IPv4 internet. So the job of the CLAT is very simple. It just maps mechanically. It's not like a true NAT. There is no state. It is stateless. The only thing it needs to know is what are the two red blocks that are configured, and then the IPv4 packet that was sent here is transformed into an IPv6 packet here. Now, this IPv6 packet has a destination address of this. This block represents the IPv4 internet, so it will end up in one of the machines that do the transition from IPv6 to IPv4. Those are called the provider address translation boxes, the PLATs. C is for customer, P for provider. Here, things will be a bit more complicated, because now this one has received, for example, a packet from this address, And now it needs to translate it into an IPv4 packet. Right? Here, it's a bit the same as the NAT problem. In fact, what we have done is, here I've on purpose used local private IPv4 addresses. So of course, this provider has more than one provider. So those addresses here cannot simply be transformed into back the 10.1.2.3 addresses here, because those are private addresses that are not valid on the IPv4 internet. But after all, that's just the problem that we always have already with IPv4, and we solve it with a NAT. So the PLAT does the job remotely that was previously done by the NAT. It's also called a carrier-grade NAT here. It's also called a NAT64, because in fact it translates an IPv6 address into an IPv4 address, but using the NAT principles here. So we know that in order to make that, we often have to manipulate the port. So this is typically what will be done. It will transform the source address, which is this one, embedded into an IPv6 address. It will transform into one of the available blue IPv4 addresses here that are allocated to this provider to represent customers like Homer. Right? The other part is easier. The other address, the destination address, that was this one. Then it's very easy because the blue part is a native IPv4 address. So the only thing you need to do is remove the red part and create a packet, an IPv4 packet that has the correct address here. Of course, while doing that, like every NAT that is stateful, you need to remember the mapping. So for example, this box will have a table that says the IPv6 address, which is this one, was mapped to an IPv4 address, which is so I guess this IPv6 address was mapped to, this is wrong, this would be 123, with a port number, that was the original port number, that was here. Then it will be mapped to another address, so this is the left part of this box, is mapped to an address on the right part. This is one of the addresses that are in this block here, and the port number may be changed here. So what we see is very simple. The PLAT here is doing the NAT job that was done here. The bad side of this solution is that the NAT job is stateful, so we need a table per customer. So having tables and table lookup is not scalable. So we have a scalability problem here. We need very, very powerful machines and many, many of them. Of course, typically there's more than one. So there is a cost in terms of infrastructure in having this solution here. So let's test our understanding. Homer sends one packet to Lisa, and Lisa responds. So Lisa sends a packet to Homer, and we observe the response at 5 here. What will we see? And the correct answer is, of course, B. Right? The IPv4 address is one of the addresses that correspond to this block here. We are sending to the NAT, like we do with a regular NAT here. Now we continue. We observe the packet at 3. And the majority says E, which is correct. B and C are correct. So here we have an IPv6 packet. And the destination address is this block with 10.1.3, so it is this one. B is correct. The IPv6 source address is also the mapped address of Lisa, which is 9.8.7.6 here. So it's not very complicated, but it's not very simple either. The keywords here are when we do this IPv4 to IPv4 per IPv6, we use XLAT, which means translation. There's no tunnel. We could have done tunneling. There has some alternative proposal that use tunnel, but here this is encapsulation which is used. Skip one of the questions, which is easy and you can discover. And the last thing we will see is the true translation. Assume here you are you have IPv6, you receive IPv6 from a provider, but there are things that are still IPv4, like Google Scholar, EPFL InfoScience, or some Skype applications that don't always fully support IPv6. So we have now the interworking problem here. So we want to do translation. And the cute idea is that the mechanism we have seen for like-to-like transport, the XLAT, can be used, in fact, a subset of those mechanisms can be used to do the job. In fact, the subset is the PLAT. We know here how to translate IPv6 to IPv4. And with XLAT, what we had, the IPv6, was itself translated from IPv6, from IPv4, but we can use if it's native IPv6. So the system is very similar, a bit simpler. We still need to reserve one block of IPv6 addresses to the IPv4 internet. This solution typically coexists with XLAT. And similarly, we need to reserve a block of addresses here in the NAT function here. And to this client, which is now an IPv6 client, it's different from a minute ago, you want to go to a server, but you are an IPv6 machine only. So the server 4, which is in fact a machine that runs on IPv4 only, but for this guy, it will appear under this address, which is an IPv6 address. That's the IPv6 that uses the prefix used by the provider to map the IPv4 world into IPv6 here. And the mapping is easy because IPv6 addresses are longer here. There's still an issue that remains. My IPv6 host wants to connect to this IPv4 server. The IPv6 host will, the first thing it will do is go to DNS to find the address of the server. But it will find only an IPv4 address. So it will not work, except if we manipulate the DNS. So in this setting, the provider plays a key role. So the provider that provides you IPv6 only access with this solution will also provide what is called DNS64, DNS that translates IPv4 to IPv6. And it will work in this way. When you connect to the DNS of this operator, when your DNS resolver connects to the DNS of this server of this operator, you ask a question, what is, for example, the InfoScience of the University of Angola in Luanda? So you ask this question, and you are doing IPv6 only, so you expect a quadruple A answer. This answer does not exist because this university, like all InfoScience, it's not because in Angola, EPFL is the same, has only IPv4 addresses here. But the DNS64 server of this provider is smart enough. It knows you are an IPv6 only client. I have to answer to you with mapped addresses. So this DNS64 is specific of this provider and is coordinated with the fact that this provider sees the IPv4 internet with this block of addresses here. So this DNS server, when it sees this query, it will ask, as we have seen, it is doing a recursive serving of the request. Stop. Whoops. It will translate this address for you by simply adding the prefix. The translation is simple, it's completely algorithmic. You add the last 32 bits to the prefix, so this guy will now know the address, and then you can connect to this, which by routing in the internet will lead you to this prefix. What this provider needs to do is inject into its routing protocol this prefix at machines that are PLATs here. Typically there are multiple PLATs, so there will be multiple of those machines that are responding to the same prefix block here. But with OSPF, we know it's possible. We can view addresses, address prefix as being present at multiple places in the network here. Voilà, that's about all we will see in terms of snapshots of how IPv6 and IPv4 can coexist. We've seen only a small number. If you're interested, you can spend pretty much all of your Christmas vacation and more studying that, which I don't recommend. I don't think it's necessary. We've seen the translation mechanisms. We have seen that they use a carrier-grade NAT, so a big super NAT, which is called the PLAT here. Other mechanisms have been translated, and in particular this one will probably be deployed also. It's a bit more complicated. It solves the problem of the carrier-grade NAT. It does similar tricks, but it makes the translation, it prepares the translation on the customer side. That adds a lot of complexity that we'll not see. And we have seen the DNS64 and application layer gateway. So typical deployment, for example, Deutsche Telekom does exactly this. A mobile operator launches IPv6 only service. Apple stuff, if you publish an Apple app, it must work with IPv6. So we don't need the 464 translation because your mobile must have all applications if an Apple system can run only Apple applications, so the problem will not exist. But we still have problems to go to IPv4 only systems, so we will use the carrier-grade NAT and NAT64. Android does not have this requirement, so you will have IPv4 services, so it will use this mechanism, and you have the CLAT that will be then a piece of software inside your Android phone. This is perhaps the most widespread deployment of all this. I will let you discover the conclusion.